Welcome back. This is Fundamentals of Micro and Nanofabrication. I'm Swayam from IIT Bangalore, and today we shall continue our lecture on subtractive processing, specifically wet etching. This will be the concluding lecture in wet etching. We shall look at some more recipes. We'll look at gallium arsenide etching. We'll look at defect etching. We'll look at some etches for metals, and we'll end off with a very interesting process called lift-off, which is often used in lithography. But fundamentally, it's an etch process, so we shall discuss it here. So let's get started. In the last lecture, we had discussed silicon anisotropic etch, and we had also discussed silicon isotropic etch. So if you remember the silicon isotropic etch, it was a three-component system. We called it the HNA where H stood for hydrofluoric acid, nitric acid, and acetic acid. And in that context, we had also discussed something called an iso etch curve, where we looked at how the concentration of these three different components affect the etch. If you want to etch gallium arsenide, which is another very popular semiconductor, the etch for gallium arsenide looks similar or is functionally similar to what the etch for silicon is, but of course the chemicals are slightly different. Now, the thing to sort of understand about gallium arsenide, and hence which can probably be generalized to most compound semiconductors, is that the etches become fairly complex if the chemistry of the material is fairly complex. So for example, if you look at this slide, we are looking at the canonical etch for gallium arsenide. And because gallium arsenide is made of two elements, which is gallium and arsenic, by the way, let me grab my pointer real quick. Because it has both gallium and arsenic, a typical phase of gallium arsenide 111, for example, are not created equal. You could probably have, you can have a gallium phase, which is often called 111A, or you can have an arsenic phase, which is often called 111B. And the difference, and the reason we have to make this distinction is because chemically speaking, whether the etchant sees gallium on the surface or whether the etchant sees arsenic on the surface leads to very different outcomes. Things are also complicated by the fact that gallium has a valency of 3, arsenic has a valency of 5. So if you were really to do the math, you can actually argue that the arsenic phase has actually more number of bonds than the gallium phase, and hence the etching rate would be different for that reason also. So if we were to combine whatever we have learned from the silicon HNA etch, there's of course the effect of the etchant concentration. In the etchant, if it's a multiple component etchant, then we have to think about what is the effect of individual etchants on the etching. But if our semiconductor is also complicated like gallium arsenide is, then we have to start worrying about which facet of gallium arsenide we are etching, what orientation of gallium arsenide we are etching, and when we are looking at a certain facet, are we looking at the gallium phase or are we looking at the arsenic phase? Now imagine you're having a tertiary material. This becomes even more complex. To cut a long story short, it becomes increasingly harder for these complex materials to find etches that are truly isotropic, that actually etch in all directions equally. That is because there is no isotropic property that you can actually use to design an etch that is isotropic. So the canonical gallium arsenide etch is also an anisotropic etch. There is really no isotropic gallium arsenide etch per se. Okay, so that's point number one to sort of remember. Okay. Now why typically the arsenic phase is much more reactive, which would mean that it etches much faster, and that is exactly for the same reason we discussed a couple of minutes ago. Arsenic has a valency of 5, so you can argue that it has 2 extra dangling bonds on the surface than the gallium phase. What that means is that the etches on the arsenic phase tends to be very smooth. Now this would come from, remember when we started looking at etching, we had discussed how some etchants are surface reaction limited and some etchants are diffusion limited. Since arsenic is more reactive, it tends to etch very fast. So these reactions are not surface reaction limited, they are diffusion limited, and diffusion limited reactions tend to produce shiny isotropic etches. Okay. So the end product looks shiny, which is often important if you're making optical devices in gallium arsenide. If you are trying to etch the gallium phase, that tends to be less reactive, and because it is less reactive, reactions often are not diffusion limited. Reactions often are surface reaction rate limited, and if they are surface reaction rate limited, they are often highly anisotropic. They may produce rougher surfaces, slightly cloudy looking surfaces, which can have impact on your optical devices. So this is something to keep in mind. So let's actually go ahead and actually look at the etch of gallium arsenide. So the canonical etch for gallium arsenide is what is called Caro's etch. It's a 3-component etching solution. it has peroxide, which is the oxidant. It has H2SO4, which is the acid, essentially the replacement for nitric acid from the silicon etch. And it has water, which is the diluent. Because we don't have HNO3, there is no need to actually have a low dielectric diluent like acetic acid was in the HNAH. And what you end up making is a very similar looking iso-etch curve, very similar to what we saw in the HNAH lecture. So I will not go into details of how to interpret this curve. You can probably look at that lecture and interpret this curve similarly. Just for now, it's sufficient to say that what you're actually looking at is concentration on one axis, changing concentration of water, on the other axis, changing concentration of peroxide, on another, the changing concentration of H2SO4. And you get these lines which represent constant rate of etchings. So along these lines are several unique combinations of concentrations, okay? And all of those combinations produce the same etching rate, hence the iso-etch, the same etch curve. Okay. The same concept that we used in the HNAH apply here too, right? So typically, if you go to one corner of the iso-etch curve, you are always waiting on the sparse components. In this case, the sparse component is H2SO4, so you're always waiting on the H2SO4. Towards this, you're always waiting on the concentration of H2O2, which is low, and that leads to different types of morphologies or different types of finishes. So in general, if you are trying to do very slow etches, you want a highly diluted system. So the diluent concentration is fairly high, and that gives you very slow limited etching, which are often reaction rate limited, which also often lead to anisotropic etches. Now, this is useful if you want to get anisotropic etches, and it's also useful if you want to delineate defects. We'll come back to defect etches later, so we shall have a more substantial discussion then. Let's focus on the other regions. So somewhere in the middle, of course, the etching rate is the maximum. This is because the concentration of H2O2 and H2SO4 both is very high. Often we don't use these regions. That is because the etching rates are not very well controlled. The surfaces don't come out clean. They often come out cloudy and not useful for microfabrication. A lot of the microfabrication often happens either in this corner or in that corner where one of the components is in short supply. So for example, if you look at here, in this case, the H2SO4 concentration is fairly high, the H2O2 concentration is fairly low, and that leads to a very viscous, thickish etching liquid. H2SO4 tends to be very viscous, and because it is in higher concentration, the overall mixture is also highly viscous. And that often means that these reactions, in this regime, you often are limited by diffusion, which gives you very nice mirror-like surfaces. Since gallium arsenide is an optoelectronic material, mirror-like surfaces are useful. So a lot of the practical gallium arsenide etches tend to focus on this region. So of course, that as we had discussed previously, Caro's etch is fundamentally an anisotropic etch. So the iso-etch curves that we saw in the previous slide are for a certain temperature and a certain orientation. So if you were to look at different orientations for a same composition, you would actually get different etch rates. So this is what this curve on this slide looks like. So let me grab my pointer again, and you see that the etching rate as a function of substrate orientation, and different orientations, say 111 versus 110, have a slightly different etch rates. And this difference is amplified, and the etching rates are also different for the A phase and the B phase. The B phase is the one that has coated with arsenic, which tends to be more reactive, and because it's more reactive, the etching rate tends to be higher. And you see, but that for all phases, or in fact for all concentration, whether it's more H2O2 or more H2SO4, you do tend to get these very anisotropy. You see the anisotropy, right? So anisotropy is from the fact that the etching rate in the 111B, which is this number, is different from 111A, which is this number. And you can also see the anisotropy that the etching rate for 111B is different from the etching rate of 110B, right? So this number is different from this number is different from this number. So you can see the anisotropy. Now if this is an isotropic etch, just like what happened in silicon, you can actually start to see this in the cross-sectional profiles of the holes that you're trying to etch. So if you again come back to this figure, you see that if you start with a mask pattern that is square, so looking from the top it looks square, after the etch you would not actually get perpendicular looking side walls. So if you look at the cross section, so if you look at the cross section from this direction, which in this case is the 1,1-0 direction, you would actually get a negative profile with an angle of around 60 to 75 degrees C. Right? So in silicon, remember the angle was around 56 degrees and it was a positive slope, right? With with the face being 111. In gallium arsenide, for this orientation, you actually get a negative slope, right? So it is broader in the bottom than it is on the top, and the angle is around 60 to 75 degrees. Interestingly, it's different from this direction versus this direction. So if you look at the same square, but in the cross section looking from this direction, which is the 110 direction, you would actually get again a positive slope. So you see the complexity of the anisotropic etching and the cross sections that you can get are significantly more here in gallium arsenide than it is in silicon, and that is because the crystal fundamentally is more complex. And to make a sense of all of this and actually visualize this in 3D becomes a little complicated. That's why you have to use simulators, and there are now these simulators that actually help you align and think of these things in 3D. Similarly, if you were to just take this square and turn it at a 45-degree angle, so now the masking pattern, this square, is not along these canonical directions, but at 45-degree angle to this canonical direction. And then when you do the etching, you would actually get perfectly 90-degree cross side walls, right? So this looks like a perfect anisotropic etch, right? Perfect vertical 90-degree walls here, perfect vertical 90-degree walls here. And what you have done, you have not changed the etchant, you have not changed the etching solution, you have not changed the substrate. All you have done is changed the orientation of the masking pattern that you are using to create the etch. Okay, so I will not go into significant more detail. This is a fundamental course. It's not a course in gallium arsenide and isotropic etching. So I leave this idea behind. The take-home message is the following. Because of the complexity in the crystal lattice, the etching rates, the etches of things like gallium arsenide are anisotropic almost always. They tend to be the etching rate changes with not just which orientation, but also whether it's arsenic facing or gallium facing. And the cross sections that you can actually get are very strong function of how the masking pattern is oriented with regarding to the canonical directions. The same square, if it's just rotated 45 degrees, will actually give you very different cross sections. Okay, so that's something to keep in mind. So let's keep going. The next concept I want to introduce is this concept of an etch stop. What an etch stop is that supposing you were to etch silicon using an etchant. So let's take you are taking silicon 100 and you are etching it with TMAH, and we know that TMAH is a or KOH is an anisotropic etch. So when you etch silicon, it will etch at this 56-degree slope, and you would keep etching. Etch stops represent some films which will not be etched by the solution that we are using. So, and in this case, supposing this dark blue layer is an etch stop. So what that means is this etching will continue happening in the silicon 100, but as soon as it reaches this dark blue layer, the etching will stop, or the etching rate will reduce so much that for all practical purposes, the etching is not happening anymore. Now you can imagine these layers are practically very useful, because they provide a sort of a feedback mechanism during the processing where you can stop the etch without having to worry about the time too much. The system is sort of stable or robust to small variations in etching rate, small variations in thickness, because beyond a certain time the material will just not etch, right? It will etch to a certain point and not etch any further. One etch stop that we have discussed is if you are doing an etching with a very selective material, say you are etching silicon dioxide on silicon using hydrofluoric acid. The hydrofluoric acid etches silicon dioxide very well, but then it stops at silicon. So silicon in that case is an etch stop to silicon dioxide etching using hydrofluoric acid. Okay. But there are etch stops that are slightly different types too. For example, in this case, the specific etch that we are actually using is a heavily doped boron layer. So this is still silicon 100. All we have done is through diffusion or through implantation, we have created this film of highly doped, boron doped silicon. Now, if you really, in a very simplistic term, this should not make sense, because after all, this is a chemical etch, and chemistry of the material doesn't change by doping, or at least not too much. So why is it that the silicon 100 that is not doped with boron gets etched very quickly, very nicely, but as soon as you add a little bit of boron, and here remember this is still ppm or maybe of 1% or 2% of boron, it makes such a huge difference that the etching stops completely. And the way we can sort of explain this is to remember the first concept we discussed when we started doing etching, that most etches are electrochemical etches. They're not just the chemistry part, it's not just about chemistry, it's also about electrochemistry. So the work function matters, and you can now easily see that the electrode potential or the work functions are very different for a highly doped silicon than it is for an undoped silicon, and that effect is enough to actually create these etch stops. Now, why are we talking about these etch stops? The reason they are is they provide, they're very useful. So for example, let's take this example again, right? So you had a wafer, it's around 400 to 500 micron thick. You start etching it with KOH, supposing the etch rate is say 100 nanometers a minute, okay? So in 60 minutes, which is 1 hour, you etch around 6 micron of this material. So of course, this means in order to go 400 micron, 400 by 6, so you need essentially 60 hours, right? Now, if you are doing an etch of 60 hours, what you do is you leave the wafer and you walk away, right? And you come back after 2.5 days. Now, if the etching times are that long, it's very, very hard to precisely stop at say 2 micron thickness, right? Because you are etching 500 micron and you are trying to stop at just exact 2 micron thickness. That's just a very hard processing problem, right? So in this case, it's much more robust, or the process is much more repeatable if it uses an etch stop rather than a timing approach, right? So instead of just trying to time an etch and etch precisely the same depth, what you try to do is you create an etch stop. So let's take the case, right? So what we want to do here is create a 2 micron thick membrane. So one student tried to do the timing approach. So canonically, the etching rate is say 6 microns an hour, but say it has a variation of, I don't know, 10%. So if it has 10%, one day it is 6 micron an hour, and another day is 6.6 micron an hour. So if it is 6.6 micron an hour, it takes very little, for the same time, your etching rates will be 10% faster. So it's very easy to overshoot and completely etch a hole and not end at a membrane. The other student was a little smarter. What they did was they first created this 2 micron thick doped layer and then started doing the etching. Now, even if the etch varies by 10%, it doesn't matter, because once the etch reaches this highly doped boron layer, the etching rate stops, the etching stops. And so even if the time is plus minus 1 hour, plus minus 10%, it doesn't really change things too much. You still roughly get a 2 micron thick membrane that you originally wanted to make. So very useful, very useful. But for this, you really need highly doped films. So we are looking at more than 10 power 20. And how much slower is the boron doped etch stop compared to the normal etching rate? So the etching rate reduces by around 20 times. Okay, so 6.6 micron an etch would become 6 micron an etch would become 0.6 by 2, around 0.3 micron an hour, which is fairly slow. Okay. So that's the basic idea of etch stop. There are several etch stops. This is not the only one. And often, if you are trying to do very fine etching, where you need to end with very thin membranes, you need to do very thin etches, it's often recommended that you use etch stops instead of just using a stopwatch and trying to time the etch. With that, let me put all of this together into an example. And the example we shall discuss is how to make a MEMS cantilever. So because this is a MEMS cantilever, it actually involves both etching, wet and dry. It involves etching of the anisotropic as well as isotropic. So it sort of encompasses a few of the things that we have discussed in etching. Incidentally, this is also a practical example. So towards the end of this course, we will actually do a lab visit where we shall see a cantilever getting made. This is exactly the same cantilever. So before you actually see the video of the thing actually getting made, it might be useful to go through the actual fabrication step by step so you know what to expect. So what is a MEMS cantilever? So as the word cantilever suggests, it's essentially an overhang. So in this case, if you're looking at the cross section, what you have is you have a silicon substrate, and the silicon substrate has a silicon nitride film on it. And what you have done is you have created this overhang. So there is a free end, there is a fixed end or a constrained end, and this free end can then vibrate. And because it can vibrate, it can do a lot of mechanical things, and then we can use that mechanical motion for a whole host of things, from sensing to actuation, etc. This is the general class of devices which are called MEMS devices. MEMS stands for micromechanical systems, and they can be on the micron scale, in this case micromechanical, or they can be often on the nanomechanical scale, which in this case is called NEMS. Okay. So the cantilever we shall focus on in this course and in this lecture is the MEMS cantilever, which is on the order of microns. So this is what we intend to make, right? So we have a silicon substrate, we have an overhang, and we have this fixed support. So we have to figure out a way to do the silicon nitride etch, right? To define the silicon nitride. So looking from the top, this is what the cantilever would look like. So this is the cross-section view, this is the top view. So you see that some amount of silicon nitride is on this fixed support, right? But then beyond this edge, this much silicon nitride hangs out. And looking from the top, it's a strip. So it's not a membrane, it's a strip. So we have to figure out a way to define the silicon nitride. We have to figure out a way to etch the silicon underneath the nitride, so you actually have this overhang, right? And of course, you need some lithography steps to define what these features are. Just one aside, so typically for MEMS devices, especially cantilevers, they are designed to vibrate at a certain frequency, and the vibration frequency is very strongly dependent upon the geometry of this cantilever. So in order to have a very precise device that exactly vibrates at a certain frequency, you then have to have a very precise control on the geometry. So that's something to keep in mind. So first thing that you would actually do is go and make this device in a software. So in any CAD software, AutoCAD will work. There are certain proprietary tools to create these files other than AutoCAD. We can also do this on something free, which is I think Clevin, or I think it's not completely free, but a semi-free or a limited free CAD software. So anyways, so on some CAD software, you first design your features. So what is our feature? So our feature is exactly this cantilever, right? And so if you zoom in one of these fields, you'll actually see the cantilever, and then this mask is written onto a mask plate. So here, this is the chrome, this is the opaque points, and then you see there are some transparent regions, and if you zoom into the transparent regions, you will actually see this pattern that you want to make. Then if you look at this cantilever, this is the process flow. So we start with the silicon wafer, which is virgin silicon wafer. There is no pattern on it. We shall create, we'll deposit silicon nitride using low pressure CVD, LPCVD. Now, because this is LPCVD and you're starting with a virgin wafer, the LPCVD actually is deposited on all hot surfaces. So it will get deposited on the front surface of the silicon wafer, but also on the back surface of the silicon wafer. So looking from the cross section, you see something like this. Looking from the top, you see something like that. Then you do the lithography using the mask that you saw in the previous slide. So the mask will create this patterned photoresist, and this patterned photoresist is now a masking layer. The exposed silicon nitride can now be etched. So after this, you would do a dry etch. So this would be in plasma. So I think the dry etch is being covered in the next module or in the module before this. I don't exactly remember, but you will get to a dry etch some point. Just take my word for it that we'll do the dry etch. So when you do the dry etch, the silicon nitride gets etched. The recipe that we shall use is anisotropic, which means that it doesn't have any undercut, right? So it exactly follows the profile of the photoresist, and it just etches vertically. So this is what you look in the cross section. This is what you look in the top. Now notice that the backside silicon nitride has not gotten etched, and that is because most dry etch tools tend to be surface facing. So the way they are mounted and the way the etching happens, the back surface is never exposed to the etchant gas and hence never gets etched. So once you are done, what you have is you have the patterned silicon nitride, but what you do not have this overhang. So remember, the cantilever must have a free end. So you need to create this overhang. So you need an etch that sort of penetrates it, etches it laterally so that you can create this overhang of this cantilever. Now you can imagine where I'm going with this, because if you want to create this overhang, then the etching must be isotropic, right? Because an anisotropic etch will never do any undercut. Here you want to create an undercut. So that's what we do. We do an isotropic dry etch, and when you do an isotropic dry etch, you actually create an undercut. So you see there's an undercut left side, there's an undercut right side, there's an undercut here, there's an undercut here. And if the undercut is severe enough, then everything underneath this photoresist will get etched, right? So everything underneath this, if you go back to the slide, everything beneath this silicon nitride layer has been etched. So what you then have is that this silicon nitride part is now hanging, it's free floating, right? There's nothing underneath it. It's being supported from one side, but otherwise it's free. So, and that is essentially your cantilever. After that, all you have to do is remove the photoresist using a PR strip, and you are left with this silicon nitride cantilever that you can use for various applications. So this is a very simple MEMS cantilever, but a very useful one, and this is what we shall look at later in the course. So here is an actual device that we fabricated, that you will see this getting fabricated in the lab course, in the lab visit. And if you look into an SEM, you can actually see the cantilevers that you have made. So you see the silicon support, right? You see the MEMS cantilever, the silicon nitride cantilever, right? We have made 3 different sizes here. And because the sizes are different, their frequencies of oscillation are different, their fundamental frequencies are different. You can actually tell that we do an isotropic etch by the shape of the etching that we are getting, remember? So we're getting sort of this spherical or smoothish looking profile, not vertical ones, because we are doing an isotropic etch. But you also see evidence of the original anisotropic etch that we did. So again, if you look at the SEM, from this side, right, in this side, you actually see relatively flat walls. So yeah, so it's a combination of isotropic and isotropic etch, and you can get the cantilever. Now some of you may ask, why is this cantilever slightly bending upwards? And think about it, it's an interesting question, and the answer is fairly simple. That is that you are trying to deposit silicon nitride. Now depending upon what conditions that you deposit it under, you would actually have a different built-in stress. And that stress could be because the film that you are depositing is highly dense, in which case it often has compressive stress. It could also be because you did the deposition at some high temperature, and when after that you cool the wafer down. So during that cooling process, the silicon nitride is trying to contract at a different rate, the silicon is trying to contract at a different rate because the coefficient of thermal expansions are different. What that means is that when you come to the room temperature, there is a residual stress, either compressive or tensile, depending upon which CT is larger, in the silicon nitride layer. So when you etch the silicon underneath, suddenly all that stress is released, and all that energy goes into bending the cantilever a little bit up, sometimes a little bit down. There are also adhesion effects. When you are doing etching, this is all dry etch, so there is no liquid involved, but you can still have some, if you are doing wet etching, you can often have surface tension type effects, which can also pull in a cantilever towards the surface or away from the surface. Finally, you see some pitting damage during etching. So we are doing dry etching. So we are sort of bombarding the surface a little bit, and that can cause some amount of damage. For MEMS devices, this damage is not very severe, so it's not a big issue. All right. So that was using a combination of anisotropic and isotropic etches to make a real device. But there are a few other etches that I would like to discuss. We'll start with what is called a defect etch. The origin of the need to define a defect etch comes from the problem that in modern semiconductors we have defects. We care about the defects. We want to see the defects. We want to understand the defects. But at the same time, we are victim of our own success. We have become so good at depositing these films that defects are far in between. I mean, the defect densities are not very high, so you are sort of chasing this needle in a haystack. There is this one defect for thousands or millions of atoms, and it's unclear whether a certain characterization technique can actually pinpoint exactly where that defect is. So it's very hard to identify where the defect is. And imagine this, you are doing this in the 60s and the 70s when the access to TM and SEM was not as common, and yeah, you couldn't like dedicate hours and hours of tool time just scanning thousands of pictures looking for that one defect. So people had to come up with some better high throughput methods to actually see the defect. Now, a lot of times these defects are small, right? So there's a dislocation, which is there, say a 2D defect, or maybe there is 1D defects, maybe there's a small precipitate. And the size of the defect is so small that optical images often miss them, right? So in a microscope, you will just not see it because the size of the defect is smaller than the wavelength you're using to image it. So you need a way to sort of enhance the size of the defect so you can actually see it in an optical microscope. And once you can see something in an optical microscope, you can go through a lot of area, because you can take a large area, zoomed image, see where the defect is, and the defect is large, so it's very visible, and then you can keep zooming in and actually finding where the defects are there. So how do you magnify the size of the defect? Using a defect etch. And the details are convoluted, and we shall not discuss them too much, but the basic fundamental is that we use the anisotropy of the etchant. So what we say is that the defect in and around the defect, the lattice is unhappy. Okay? Because the lattice is unhappy, it can actually have a slightly different etching rate at the defect site than at the rest of the bulk crystal. And that difference in etching rate can be used to either create a hillock, in which case the defect doesn't etch and the rest of the material etch, so you create a hill, or to create a pit where the defect etches very fast and the rest of the material doesn't etch, so you create a pit. So either by using hillocks or by creating pits, you have now created a slight morphological feature. And this feature is bigger than the defect because the stress created by the defect is a little larger than the defect itself. Okay? And that large thing can often be, say, a 1 micron in size, and hence visible even under an optical microscope. What sort of defect etches are used? Well, there's a whole library of defect etches. So if you look at the slide, you can actually see some of the more popular ones. So very old is a dash, what is called a dash etch, and that is just a modified HNA etch. So this is an isotropic silicon etch, and this is a one where it's a very dilute solution. So the A part is large, and it's a very dilute solution of hydrofluoric acid. There's a lot of nitric acid. So this composition, somebody found, the person's name was Dash, that's why it's called a dash etch. So Dash found that this etch can be used to delineate defects in silicon. The only problem with this etch was that it takes very long time to actually show defects. It takes like 8 hours, so essentially overnight. Slightly more modern etches tend to not have nitric acid as the primary etchant. They tend to have chromic oxide as the primary etchant. So you still have an HF and chromium oxide solution in water, where water is the diluent. But instead of nitric acid, you have chromic oxide. So there's a whole bunch of family of chromium oxide based etches, right? So these, for example, these two, yeah. So Sertel, Seco, I have not mentioned Schimmel, but Schimmel etch is also a chromium oxide based etch. And the advantage here is that you can see the 111 and 100 facets, and the etching times are fairly small. Now, another class of etching compounds are which use both HNO3 and chromic oxide. So here's an example of a right etch. It also uses some copper nitrate. Now you can sort of see that some of these etches are fairly complex, right? It's very hard for you to identify what is a mechanism. There is some method in the madness, but by and large, defect etches become more art than science. It's very hard, even if you read the original papers, they don't exactly pinpoint exact mechanism not understood. Maybe there are some intuitions that the author had, but those are not often shared. So it's very hard to know what exactly is happening and why does this defect etch work the way it does. You just use these as ready recipes, and yeah, as I said, it's more art than science. So the advantage of the right etch, for example, was that it had long shelf life, it didn't degrade, so you can actually make a right etch solution and keep it in your fridge. There are also some silver nitrate based systems which are called silver etches. There are some bromine based systems. Some of these bromine based systems, for example, can distinguish between gallium arsenide A and B phases, which is very important. As we discussed, the etching rates are very different for these two facets. You can, for example, use the HF-HNO3 etch to delineate PN junction. So you have a P-type material, N-type material. If you want to see where the line is, you can actually use this etch to find that. If you are growing epitaxial films using CVD, the silver etch is very, very useful. Okay, so defects that tend to happen in epitaxial growth are amplified by using this defect etch. The last point I would like to make about the defect etch is the fact that most of these chemistries are not CMOS compatible, right? Chromium is a contaminant, it's an impurity, we want to avoid it. We did so much cleaning in the start of this lecture, right? So if you are using these defect etches, please use separate labware. Do not contaminate your CMOS grade labware that you're using for everything. Samples that have been used for this chromium based etch must not be used for anything else. So this is a destructive etch, if you may. So once you use that sample for the defect etch, do not use it for your device fabrication. It's contaminated beyond repair. All right. So here are some of the references for each of the etches we just referenced. You can look at it on your own time. Finally, some metal etches. So this is another very important part. Metal etches are often used. Wet etches is often used to etch metals. By and large, you are just using either an oxidant or an acid to etch a metal. So for example, for aluminum, the common etchant is hydrophosphoric acid and HNO3, and it etches at around 150 to 100 nanometers a minute. Gold becomes a little more tricky. Gold is a noble metal, so it doesn't etch with most etchants. You can of course use aqua regia, but the problem with these very strong etchants like aqua regia is that you cannot use it with photoresist. So that becomes a challenge. Thankfully, there are some iodine-based gold etchants that actually can be used with the photoresist. So if you have to pattern gold, maybe you have to use this. Let me actually finish with something like platinum. Something like platinum is an example where you cannot etch it with any etchant that will not destroy the photoresist. So the only etchant available is aqua regia. Aqua regia is not compatible with photoresist, so you cannot pattern and then etch metals. So if that is the case, how at all do you pattern those metal layers? So what you do is something called lift-off. So in 2-3 slides, let me just talk about lift-off. So the basic idea of a typical patterning step is that you take a substrate, you take a film, you deposit photoresist, and then you pattern, and then this exposed film gets etched, and then you get your patterned film. Now this of course would not work if the film is platinum, because there is no etchant that will not attack photoresist but attack platinum. So what people do is something called lift-off, where they define the inverse pattern. So the photoresist is where you don't want platinum to be. Then you do the film deposition. So platinum is deposited after the photoresist. And then when you remove the photoresist, all the unwanted parts of platinum just float away. So we only get platinum deposited where there is no photoresist. And of course, in this case, there is no etching, right? You just lithography, deposition, removal of photoresist. There is no etching step. But however, this seems very easy, seems very the thing to do, but there are some challenges. So this is the ideal case that you hope to expect. Sometimes what will happen is you will get sidewall depositions. So if you get the sidewall depositions, then it's unclear when this photoresist goes away, how will this film peel, right? So you typically won't want this to happen. So often we prefer depositions which are directional deposition. We don't prefer depositions that are conformal. So prefer evaporation over sputtering. Second thing is you may remember from the photoresist lectures, the lithography lectures, that photoresist profiles are not exactly 90 degrees, right? They depend on so many other factors. So you can get profiles look like this, you can get profiles look like this, and these two profiles would get you very different looking metal films, and that has an impact on how lift-off happens. So you have to be careful. Some of the problems that people have when they do lift-off is you actually get retention, where you get some film where it shouldn't be. Sometimes you get ears, which happens when you actually have a conformal deposition, so the sidewall metal remains. You can get overdevelopment where metal peels off from places where it should be deposited. Or sometimes you just get redeposition, where some metal actually floated away from this portion, but then it remained in the solution and at some point fell back on the surface. So often you start to sort of see these defects when you look at your images. So this is why lift-off is a little tricky or a little non-repeatable process, but it's required for things like platinum. So one way you can actually enhance the success of your lift-off is actually to try a lift-off resist. So what is a lift-off resist? So you just look at the figure. So simple resist is you have a substrate, you have a photoresist, you shine UV light, you pattern the photoresist, done. What you do in a lift-off resist is a lift-off is not a photoactive material. You deposit it between the photoresist and the substrate. You do your do the patterning, you do the development. During development, the photoresist develops normally. But the lift-off resist is designed to isotropically etch. So when it isotropically etch, it undercuts. So what you get is you get this undercut in the lift-off resist layer. So instead of getting a profile of photoresist that looks like this, you get a profile of photoresist that looks like a T, right? And you can imagine this T is much better for lift-off because there is no danger of sidewall deposition. So for example, here are some actual figures from the manufacturer of this LOR resist. So this is what you'll see, the undercut in the LOR. You see the photoresist on the top. And of course, you can have different cases, right? So if you etch for longer, the undercut increases. So the shape of this T, the base of the T becomes more narrow and the overhang becomes more long. You can also change the thickness of the LOR. So this is an example where the photoresist is thin, the LOR is thick. This is an example where the photoresist is thick, but the LOR is thin. So depending on what your application is, you can actually make any sort of profile. Is that when you do the metal deposition on this T shape, if you look at the edges, there is no conformal deposition, right? There's always a crack here, and that crack is because the photoresist is not continuous. And this crack allows you to do a cleaner lift off than would be otherwise possible. So that is why if you are having trouble with your lift off, if your lift off features are very small, you may consider using a lift off resist to improve the fidelity of your process and repeatability of your process. Okay. So with that, we come to the end of the etching lecture. This is the end of the subtractive module, the wet etching module. I'll see you towards the end of this lecture again, where we shall have one lecture on process integration. So I'll see you then.